Welcome to Chemistry 112. Today we'll be starting Chapter 19, Electrochemistry. It's going to reach back into, it's going to start with some new material. Some of it, maybe you remember when we first talked about oxidation reduction reactions in general chemistry, like chapter, depending on which book it is, like chapter 5 or chapter 9, something like that. But it's the one where we started talking about net ionic reactions and combustion reactions and single replacement and double replacement, all those stuff. It's going to also touch into our Gibbs free energy again. It's also going to touch into our equilibrium expression again. So it's going to nicely wrap up all the material, essentially. It's in some ways a little different in that how you're going to calculate E cell is maybe a little different from how we've ever done these other things, but it's going to be different in a way that's easier. I have the tests done, graded. You can come by and get them at any point. Technically, there's one still out, not done. I told that person, hey, do it by Wednesday. Told them on Saturday and Sunday, hey, come do it. Told them on Tuesday. On Monday, come do it by Wednesday. Haven't heard back from them. So I'm going to just assume they're either dropping or going to fail. So not much that can be done about that. Chapter 19. Now, Chapter 19 is all about oxidation reduction reactions to some extent. So the first thing we should do is to remind ourselves what they are, because not everyone has a photographic memory that can call back first semester one little bit where we talked about reactions where electrons got transferred. So oxidation reduction reactions are reactions where there's electron transfer. And one of the key components here is the oxidation number of an element will change. If there is and much like in acid-base chemistry, if there was an acid, there must be a base. Otherwise, it's not an acid action. Well, in oxidation reduction, if there is an oxidation, there must also be a reduction. The same way in Gibbs free energy, we talked about the first law of thermodynamics. If heat is produced, it had to go somewhere. Or if electrons are released, they have to go somewhere. So we're always going to have a pair. Someone's going to lose electrons, someone's going to gain electrons. One element is going to go up in charge, one element is going to go down in charge because the electrons are conserved. So let's remind the definition of oxidation. Oxidation is the loss of electrons. Because electrons are negative, anything that is oxidized has to become more positive. Now, more positive typically means it could be going from more negative to less negative, like -7 to -5, or -4, or -3, -1. It could be going from -1 to 0. Could be going from -1 to +1, or +1 to +3. But the idea is becoming more positive, less negative. An element that is oxidized will sometimes be gaining an oxygen or losing a hydrogen. For those who will eventually have to take organic chemistry, when we talk about oxidation in terms of organic chemical reaction, oxidation usually occurs the addition of oxygens. So we're going to lose a carbon-hydrogen bond to make a new carbon-oxygen bond. The best situation, the most obvious situation, is conversion of methane, which is CH4, to carbon dioxide, which is CO2. Both of those are double bonds. We've lost 4 CH bonds. We've gained 4 new CO bonds. 2 of them are single bonds, 2 of them are double bonds. That's combustion, which is the most quintessential type of oxidation reaction. Reduction is then just the opposite. We're reducing the charge. The element is becoming more negative. If it's organic, it may be losing an oxygen. It may be gaining some hydrogens. That's often a way we can reduce something in organic chemistry. Now, an easy way to remember this is oil rig, the mnemonic oil rig. Oxidation is loss, reduction is gain of electrons. There's also a mnemonic of Leo the lion says grr, where losing electrons is oxidation, gaining electrons is reduction. Use what you need to. It doesn't really matter. Use what you need to get to remember this. Now, you have to remember there's certain rules to determine oxidation states, but we can make our lives a little bit easier. One rule is oxidation numbers of pure elements. Whether this is a singular element or diatomic element, if it is a pure element in the standard state, it is 0. So that means zinc solid is 0, but oxygen gas is 0. That means sulfur S8 is 0. That means Buckminster fullerene, which is C60, is all 0. All the elements in there are 0. It's just carbon. Oxygen, when it's within a compound, is usually 2-. The one exception is, well, technically there's 2 exceptions, but the one major exception is peroxide. Hydrogen peroxide is the most common way. But usually that's going to be defined, and you'll be able to figure it out that it's hydrogen peroxide. But almost every other time, oxygen is 2-. So we're going to treat oxygen as 2- when it's in a compound. Hydrogen is almost always +1. If it's, as long as hydrogen is mixed with a non-metal, it is going to be +1. If hydrogen is mixed with a metal, then it could be its rare case -1. But in all other cases, it's +1. And 90% of the time, it's going to be +1. Pretty much every other element can be determined via context. However, there's like, halogens are usually -1, and group 1 metals are usually +1, and group 2 metals are usually +2. But oxygen and hydrogen will usually get you there most of the time. So breaking down this first equation, zinc plus oxygen. So zinc is oxidized to form zinc oxide. Zinc starts at 0. And if we look at the other case, we see oxygen plus zinc, so zinc must be 2+. So zinc starts at 0, goes to 2+. Zinc is losing electrons. Zinc is then must be oxidized. Oxygen starts at 0, goes to 2-. Oxygen is being reduced. Now, here's part of the trickiness of here, the verbiage, that you still need to be able to understand some basic English to get this. That because zinc is oxidized, and oxidation and reduction always come in a pair, that zinc must be reducing oxygen. Zinc must be performing the act of reduction on oxygen. So it can be referred as a reducing agent or a reductant. The guy who gets oxidized reduces something else. The guy who gets oxidized reduces something else. So we can call it a reducing agent. Now, the same way with oxygen. Oxygen is being reduced, but it is oxidizing zinc. So oxygen is the oxidizing agent or the oxidant. Now, more often than not, oxygen is an oxidant. Thus, the whole reason why we call it oxidizing, because it's coming from the root word oxide. It's coming from oxygen. Now, some types of reactions we'll see are disproportionations. They occur when the same element is both oxidized and reduced, and that can happen. That can happen where, in this case, this is hydrogen peroxide. This is that one rare case that I talked about. H is +1. Each oxygen is -1, so that 2 pluses and 2 minuses cancel out to have a net charge of 0. So we have 1 plus and 1 minus. Now, this is going to go from 1 plus and 1 minus to 1 plus and 2 minus, and 1 minus to 0 to 0. So one set of oxygens are going to 0. They're losing each 1 electron. And one set of oxygens are each gaining 1 electron. In this case, oxygen is both being oxidized and reduced because we're at an intermediate step. We're somewhere between stable oxygen and stable water, and so it breaks apart. And this actually is what happens that makes hydrogen peroxide go bad over time. We typically put stabilizers in our peroxide to slow this process down, but over time, hydrogen peroxide will naturally decompose into water and oxygen. And if you've ever watched the elephant toothpaste reaction, we just catalytically speed this up. We just add a little bit of catalyst that makes it all break down all at once, and you try to capture most of that into bubbles, which then shoot out as foam. Now, the first thing we can do is balance redox reactions. Now, to understand redox reactions, we have to break them down into the 2 half reactions. We're going to break them down into the oxidation half and the reduction half. Because one thing we've never really worried about before is the electron count, because the electrons never really change. If you look at a reaction as a whole, you may not readily realize that it may look balanced on its face, but in reality, it's not balanced because of this oxidation nonsense. The idea here is that the electrons lost on one side of the reaction must equal the electrons gained on the other. And so to do this, we're going to split it in half. The oxidation, where electrons are lost, will have electrons as a product. Reductions will have electrons as a reactant. But eventually, we will combine them back together to form an overall equation. Now, when we look at this, we look at a simple 2-element reaction. We can split it into 2 half reactions. Now, this is not perfect, but so I'm splitting up my zinc oxide into zinc 2 plus and oxygen 2 minus. This one's obvious. It needs to be balanced. And this one, you don't actually have to do this to balance it. But what we're going to do is split it up. So zinc goes from zinc to zinc 2 plus. You go oxygen to oxygen 2 minus. The first steps we're always going to do is we're going to balance the elements. We're going to balance the elements. Then we're going to add charges to balance the charge. So what you want to see is the same charge on the left as on the right. The same charge on the left as on the right. For the zinc, you see 0 on the left, 2 plus on the right. The problem is you can only add electrons. You can only add electrons. So we can't ever bring 0 up to +2, but we can bring +2 down to 0. By adding 2 electrons, we balance this guy. Now, with oxygen, we have 0 on the left, 4 minus on the right, because we have double oxygens. We can't ever bring 4 minus up to 0, but we can bring 0 down minus. So 4 on the left. Now, one thing that we're going to do when we combine these back together is we have to have the total number of electrons on both sides be equal. So if this has 2 electrons and this is 4 electrons, what we're going to have to do is double the number of electrons. So you'll double the zinc. So you have 2 zinc plus electrons. 4 electrons, 4 electrons. The 4 electrons will cancel out. So when we put these back together, we would get 2 zinc plus oxygen plus 2 zinc oxide. Now that one's kind of stupid, but we'll see sometimes it's not as clear. Looking at this problem, tin 2 plus iron 3 goes to tin 4 and iron 2. On its face, that looks balanced. There's 1 iron, there's 1 iron. There's 1 tin, there's 1 tin. However, if you look at the total overall charge, the charges are not balanced. We go from 2 plus 3, which is 5, to 4 plus 2, which is 6. You have 5 plus on the left, 6 plus on the right, meaning there's an electron that has disappeared into the ether somewhere. So this is not actually balanced. So we have to figure out and fix that. So we're going to split this. Tin 2, tin 4. Iron 3, iron 2. Then we look. Are they balanced? Yes. 1 tin, 1 tin. 1 iron, 1 iron. Now we add the electrons. Tin 2, tin 4. 2 electrons brings 2 plus, 2 plus. Iron 3, iron 2. 1 electron brings it from 3 to 2. Now, the greatest common factor, the multiple between 2 and 1 is 2. So we are going to just have to double the irons and then add the equations together. Everything on the left of the equation gets added together, and everything on the right of the equation gets added together. We get tin 2 plus 2 iron, 4, and 2 iron. If we add the charges, 2 plus 3 is 8. 4 plus 2, also 8. The total charge on the left is 8. The total charge on the right is 8. Now, what is more often the case is acidic reactions. Reactions that are far more complicated because they have acid and water, and we have to go a little bit further. Now, this is a bit different from how the book wants to teach it. But honestly, I think this is, if anything, way easier. But doubt me, go ahead, look up what it says in the book. I think this is pretty easy. Well, I'm going to lie. No, I don't think this is pretty easy, but I think this is easier than the book method. So we're going to break it down into these 7 steps. Once again, on a test, if I throw one of these questions out on you and you have a cheat sheet, write down the 7 steps. Write down an example of how to do this. It is You have an example in front of you. It's not going to, you can hopefully replicate it. But step 1, we split the reaction into its half reactions. Step 2, we're going to balance the non-hydrogen, non-oxygen elements. Step 3, we're going to add water to give you oxygens. Step 4, we're going to add hydrogens to balance the hydrogen. Step 5, we add the electrons. Step 6, we find the greatest common factor. And step 7, after we add them together, we cancel things out. So I'm going to write these down and actually work this out. I mean, I have it worked out on the notebook, but I'm going to work it out in my doc cam so we can maybe better see this. But it's all here. So if you miss this, it'll be there. Okay. So step 1, we split them into the half reaction. So we have 1/2, the permanganate goes to Mn2, and we have the carbonate, the oxalate, oxalate going to CO2. That's my step 1. Step 2 is I balance the elements. So in this case, Mn. So this one can stay as written. I don't have to balance this. It is good. This guy, we have 2 carbons on the left, and we have 1 carbon on the right, so I would have to double the amount of CO2. So that's step 2. Step 3, we are going to balance the oxygens by adding water. We're going to just add water because, remember, all of these are going to be done in an aqueous environment. So we can say there's water that's going to actively participate in this reaction. So 4 oxygens here, 0 oxygens here. What do I have? 4 waters. 4 oxygens here, 2 times 2, 4 oxygens there. So this guy doesn't have to be touched. The oxygens are already balanced. Step 4, now I've created a disturbance by adding hydrogens. So I have balanced the other side by adding H+, protons. We're going to assume this is, what did we learn in the acid-base chapter? If there is water, there is acid, there is base. There is going to be a natural abundance of acid because water can break apart into acid and base. So 4 times 2, there's 8 hydrogens on the right, so I need 8 hydrogens on the left. Two plus 4 waters. This guy can still be kept the same because there's no hydrogens involved. Now, step 5, balance the charge. So 8 plus 1 minus, this is a net charge of 7. This is a net charge of 2 is 5. We need to add 5 electrons to the left. H plus MnO4 minus plus 5 electrons goes to Mn2 plus and 4 waters. This guy is 2 minus. This guy is 0. So we're going to have to add 2 electrons to the right. Now, the greatest common factor between 5 and 2 is 10. 10. So we're going to have to multiply this guy by 2, and this guy by 5. It's not pretty. So we have 16H plus, 2 MnO4 minus, plus 10 electrons, goes to 2 Mn2 plus and 8 waters. And we have 5 C2O4, 2 10 CO2s, and 10 electrons. Now step 7 is we add both reactions together. Everything on the left side of the arrow gets added up. Everything on the right side of the arrow gets added up. 16H plus. It doesn't really matter the order. The order doesn't matter. 2 minus, 10 electrons. Right side of the reaction. 2 Mn2 plus, 8 waters, 10 CO2s, 10 electrons. Now, here's the important thing before we finish. Everything that is identical, left and right, gets canceled out. There's no H pluses on the right, so you don't worry about that. There's no MnO4s on the right, no C2O4s on the right, but there is 10 electrons, 10 electrons. So they get canceled out. Now let's look at all the things. There's 16 H's. There's 8 times 2, 16 H's. There is 2 Mn's. There's 2 Mn's. There's 10 C's. There's 10 C's. Now here's hard. 2 times 4 is 8. 5 times 4 is 20. There is 28 O's. 8 times 1 is 8. 10 times 2 is 20. There's 28 O's. And here's the last thing. For the negative charges. How many negative charges are there? What is the total charge? 16. 16 plus. 2 minus. 10 minus. The net charge here is positive 6. That's 2 times 2 is 4 plus. What did I do? Oh. I'm retarded. Gotcha. That's 4 plus. 16 minus 2 minus 10 is 4. And this is 2 times 2 is 4 plus. So the net charge on the left is 4 plus. The net charge on the right is 4 plus. The charges are balanced. This reaction is entirely balanced. That going about it and trying to balance this guy on its own without splitting it up is downright near impossible. Doing it in this systematic way, it's long, it can be tedious at times, but it is very much so doable. Now, how the book would have you do it is you would have to actually determine the oxidation state of manganese on the left as 7 plus and determine it on the right as 2 plus. And then that can be your guide for adding electrons. However, my way doesn't require you to actually know the oxidation state of manganese. You can just use the charges to find it. My way didn't make you find out that carbon was 4 plus on here and what, like 4 plus and then 8, 3 plus, be 3 plus there. You won't have to figure that out. because of the method I'm trying to use. So use that to your advantage if you can. Do another practice problem. This one, we might have stuff canceling out. H2O2 plus chromium 3 plus goes to water and dichromate, Cr2O7 2 minus. Okay, so we'll work this out on the doc cam. I'm just writing this down so I can better do this. Sorry. Step one is to split this apart. H2O2 goes to water. And chromium goes to dichromate. Okay. There's no hydrogen, there's no non-hydrogen, non-oxygen elements there, so I'm not going to balance that. There is a chromium, two chromiums there, so I'm going to double that. The second step, I'm going to add waters to balance the oxygens. Now this guy goes H2O2, so I'm going to balance that with 2 waters. Oxygens on the left, 2 oxygens on the right. Now this guy, you'll notice this guy, we have to balance it on both sides. So we have 2 chromiums, but there's 7 oxygens, so I'm going to add 7 waters here. So 7 oxygens, 7 oxygens. Now that's step 1, step 2, this is step 3. Step 4, now I'm going to add hydrogens. There is 2 times 2, 4 hydrogens. There's 2 hydrogens. So what do I got to do? I have to add another 2 hydrogens right here. H2O2. So this whole thing looks like that. And I'm going to go ahead and put step 5 and add in the electrons. So that's 2 plus, that's 0. So we're going to have to add in 2 electrons over here. Now this guy, there are 7 waters and 2 chromium goes to Cr2O7 2 minus. And this is 7 times 2 is 14. There's 14 H's, so I'm going to have to add 14 H's. You got a big number here. Now let's look at the charge. 2 times 3 is 6. 14 minus 2 is 12. What do I got to do? I have to add 6 electrons here. 6 electrons here. Chromium is actually 6 plus in dichromate, and it's going from 3 plus to 6 plus 2 times. Now, how do I add these together? How do I add these together? Well, the greatest common factor between 6 and 2 is 6. So what do I got to do? I have to multiply this whole side by 3. What am I going to get? I'm going to get 6 H pluses, 3 peroxides, 6 electrons goes to 6 waters. And this is just going to stay 7 waters, 2 chromiums, 1 dichromate, 14 protons, and 6 electrons. Okay, now becomes the hard step of adding them together and canceling out. Here's why you need to be careful when you're canceling out. So let's add all the left sides. So 6H plus. 3 peroxides, 6 electrons, 7 waters, and 2 chromiums. All that on the top. On the bottom, 6 waters, dichromate, 14 hydrogens, or 14 protons, 6 electrons. Now here's the thing. Everything that appears on left and right, or in this case top and bottom, gets canceled out. So we'll start with the obvious one, 6 electrons. Now here's the less obvious one. 7 waters, 6 waters. 6 of those 7 waters get canceled out. So that goes down to 1 water. 6 protons and 14 protons. That goes down to 8 protons. Everything that can be canceled out has now been canceled out. So the new equation is 3 peroxide plus water plus 2 chromiums goes to dichromate and 8 hydrogens. How does this differ from my original starting equation? Starting equation had water as a product. Now suddenly water is a reactant. Where's our source of oxygen? Where's our source of oxygen? This guy's going from -1 to -2, but where is it going? Where's that oxygen going? Where's that -2 oxygen going? It's going into the dichromate. That source of oxygen. This is going from -1 to -2. It's doing that 6 times, and that water is adding the additional hydrogen, the additional oxygen to make it 7. So you would never have figured that out by trying to balance that equation unto itself. You can only do it by splitting it up and solving them separately before adding them back into each other. So it's just a systematic approach. We split it up, we balance each one, and then we find the greatest common factor and add them back into each other. I know it's not easy, but it's something we can do given a little bit of practice. Given a little bit of practice. So now, how do we treat basic situations? So we're going to treat basic situations just the same as we treat acidic situations, except at the very end, we are going to add in base to both sides. And one thing we'll have to remember, when we add, this reaction works. When we add H plus and OH minus, it's going to produce water. This is the key component here. When we add H plus to OH minus, we're going to form water. So let's separate this. HO2 1 minus, that's I'm trying to remember what that is. It's not, it's like it's not hydrogen peroxide in itself because it's a peroxide anion of some sort. But the fact of the matter is, okay, that's going to base, and the other side is H2SO3. Sulfurous acid is going to hydrogen sulfite or hydrogen sulfate or bisulfate. Okay. Step 1, we've split it. Step 2, S and S, they're balanced. We don't have to balance anything there. Step 3, we add water to balance the oxygens. We still do that. HO2, 1 minus, OH, 1 minus. We add water. Now we have 2 oxygens, 2 oxygens. H2SO3, HSO4, 1 minus. We're going to add a water. 4 oxygens, 4 oxygens. Step 4, we add hydrogens. We have 2, 3 hydrogens on the right, 1 hydrogen on the left. We are going to have to add 2 protons. Now, as I said, we could be adding base in here at this point, but it's going to make this a whole heck of a lot more complicated, because when we add base, we're adding an O and an H. An O and an H, and it makes it a whole heck of a lot messier when it comes to try to balance this guy. So we're going to add H, and we're going to fix it later. But okay. 2, 4 H's, 1 H. So I have to add 3 H's on the right. So 4 H's, 4 H's. Step 5, we're going to balance the charge. 2 plus, 1 minus, that's a net of plus 1. That's a net of minus 1. How do we get from plus 1 to minus 1? We add, I'm going to just put plus 2 electrons. Neutral, neutral, this is 0. 1 minus plus 3 is 2 plus. How do we get from 2 plus to 0? We're going to add 2 electrons on the right. So the greatest common factor is 2 and 2. So we don't have to do anything there. So for 7, we're going to just add these guys together. We have 2H plus, HO2, 1 minus, H2SO3, and H2O. Goes to OH minus, water, HSO4, and 3H plus. Okay. We'll start by canceling everything that is the same on both sides. We have 1 water. We have 1 water. We have 2 H's. We have 1 H. Now, you could either make the math work and make this into a water, or you could do it like this. So we're going to add 1 OH to both sides. For every H plus, we're going to add 1 OH to both sides. So there's 1 H plus, so I'm going to add 1 OH. For every time you add an OH to the H plus, that becomes water. So now let's rebalance it. HO2, 1 minus, H2SO3, and OH minus goes to OH minus, HSO4, and water. Well, now we have an OH minus on both sides. I can cancel those out. So our overall equation is HO2, 1 minus, and sulfurous acid goes to HSO4, 1 minus, and water. Now, this one didn't really matter whether it's going to be in acidic or basic conditions, because you would still have the net overall effect. But sometimes acid, 1 minus, 1 minus. We have 1, 2, 3 hydrogen, 1, 2, 3 hydrogens. We have 1, 2, 5 oxygens. We have 1, 2, 3, 4, 5, 1s, 1s. Everything is balanced. The reaction is done. So that is at least a small part of this chapter. I'm not going to say it's a huge part because the main part is about voltaic cells, but occasionally you do need to know something about how to balance the chemical equation to figure out what is going on. What is going on in this overall reaction? Because we're trying to understand this in terms of half reactions. But how do we actually make sense of this? How do redox reactions typically get used? Well, besides in nature, we use it in our body all the time. We oxidize this, we phosphorylate that, we change the charge, we move electrons around, we create proton channels, we form ATP, we burn stuff, and we get some energy when we do this oxidation reduction reaction. But the way we typically see this in its the simplistic form, in the most directly observable form, is batteries. What a battery actually consists of is essentially a series of half cells, a series of 2 half cells repeated numerous times. We repeat it numerous times to get a specified voltage. We want to increase the voltage by, or increase the energy density by doing it more and more and more times. But essentially, we have a series of 2 half reactions that will produce an electrical energy, what's referred to as a voltage. Now, a voltage is capable of doing work. Remember back to our internal energy is heat plus work, and there are supposed to be other energies like electrical energy that we kind of simply ignored because most things aren't oxidation reduction reactions. But when we have oxidation reduction reactions, we do get electrical energy. Now, batteries are called voltaic cells, often called galvanic cells, named after early electrochemists like Luigi Galvani or Alessandro Volta. But essentially, these are cells that consist of 2 individual cells with a conducting fluid and electrodes. So 2 half reactions are going to occur in a solution. There's going to be some sort of solvent that's going to let the reaction work. There's going to be electrode that's going to connect these 2 together so that we can pull energy off. And finally, we're going to kind of have a salt bridge. We're going to connect it on top with an electrode and a wire, and on bottom with a salt bridge to create a completed circuit. If you've ever heard of like why electricity won't flow and not to pick up a live wire, is because you don't want to complete the circuit. It's going to have a round return trip loop. And if any time the round trip is blocked, there's a roadblock in the way, there's something cutting the wire, electricity doesn't flow. Doesn't matter if everything else is connected, electricity won't flow. But if you pick it up, there's a chance you are connecting the circuit to something else, whether you pick up both ends of the wire or you're just grounded into the ground, electricity can flow through you, which is part of the danger. Now, 1 half cell will be the reduction, the other half cell will be the oxidation. But if we are missing any one part of this, the battery will not function. Back at Purdue, we used to make our own little batteries as one of the labs. We made a small little like electrode this and dipped it into there, and it had a sensor, and people would sometimes have problems with it. My little battery thing isn't working. And more often than not, the problem was, like for example, their salt bridge wasn't connecting one solution to another. Like they somehow got an air bubble stuck in their battery, so that the salt bridge was, instead of touching the liquid, it was touching air. And so in the long run, they didn't complete the circuit, and so it didn't work. Even though everything else was perfectly fine. They had the electrode, they had the solution, they had the half reactions. Because they didn't complete the circuit between the salt bridge, it wouldn't work. Now, these cells are going to be divided into what we call the anode and the cathode. Now, anode is our negative. Remember, it sounds like anion. Cathode is our positive side. It sounds like cation. Now, the anode is where the oxidation occurs. The easiest way to remember that is that anode and oxidation both start with vowels. Cathode is where the reduction occurs, where both start with consonants. But if you think about it in terms of chemistry, you can also reason it out. Anode is negative. Electrons are negative. What happens when you try to bring two negatives together? They repel. Electrons will flee the anode, flee the negative, and run to the positive. So electrons are going to leave, which is oxidation, and they're going to be gained at the positive, which is reduction. So looking at this wire diagram over here, the electron is fleeing that wire, going to the positive side. Now, however, when you do this, you're going to create a charge buildup in solution. Zinc is going from zinc to zinc 2+. You're going to start building up more and more positive in solution, more and more positive in solution. And this one's going to be losing positive. Copper is going to go from copper 2 to copper solid, and it's going to build up a negative charge in solution. And this is going to slow the reaction down as the zinc electron dissolves and the copper electron deposits. So the salt bridge is there to try to keep the charge the same. As the positive charge goes into solution, some anions are going to flow from the salt bridge. A salt bridge is just a kind of like salty string. You dip it in like a salt water solution, and it gets stuck with salt, impregnated with salt. And so the salt can flow through this little string into the solution to make the positive and negative cancel out. And then the positive cations can flow into this solution over here on the right and replace the positives that are leaving, keeping the net charge of both the same. But one of the key things is a voltaic or galvanic cell will always occur in a spontaneous direction, doing the work. It will always produce work. The entropy of the universe will always be increasing in a voltaic or galvanic cell. And it's always written anode first. So when we write this, this would be a zinc to copper situation rather than copper to zinc, because zinc is our anode. It's by thing. And if there are several, here's one of the important things. When several reactions are possible in a voltaic cell, the largest one will always occur. So if you're wondering why, for example, we cannot do a certain reaction, it's because maybe we have an impurity that's going to get oxidized first. You have water. Maybe water is easier to oxidize than your sample, in which case you're going to do the water first. This is the same idea we're going to get to later when we talk about galvanized steel. Galvanized steel, we put iron, which is easily oxidizable, and coat it with zinc, which is even more easily oxidizable. So that if oxygen has a choice to attack iron or zinc, it's going to attack the zinc first. It's going to protect the iron, and it's going to keep the integrity for longer because we can have it attack zinc instead of iron. It's going to do the largest one first. Now, when we write these guys, we can often write it in shorthand notation, so we don't have to draw the whole dang structure out. They're often written with this single dash and this double dash. The single line separates the electrode from the solution. The double line separates the two half cells. So we can describe that whole cell by the whole battery by this little thing. All components will be described, including their concentrations, except for the salt bridge, and anode first. So we're looking at this, we're saying a zinc solid electrode is dipped into 1 molar zinc solution. And on the other side, 1 molar copper solution is dipped into copper electrode. So zinc is going to zinc 2 plus, copper 2 plus is going to copper solid. Now, if the electrode is not part of the half reaction, so sometimes both the reactant and the product are solutions, are aqueous, or maybe the product is a gas. You can't conduct electricity through a gas, so how are you going to manage that? Well, sometimes you're going to have to use a non-reactive conducting electrode, such as platinum or graphite. So one of the reasons platinum is so expensive is because it's typically not reactive, and so it's used for in a lot of different chemistry. So for example, if I'm doing fluorine gas and iron 2 plus goes to iron 3 plus and fluoride, I would have on one side the anode, the oxidation. You would have platinum solid, there's my electrode. We have 1 molar iron 2 plus and 1 molar iron 3 plus. So iron 2 plus is going to 3 plus. On the other side, 1 atmosphere of fluorine gas, 1 molar fluoride. So fluorine gas is going to fluoride, and we have a platinum electrode to work that out. So essentially, I'm bubbling fluorine into solution, and it's going into solution. And iron solution is going from one state to the other, but it's still staying in solution. And the platinum is just there to conduct the electrons from one side to the other. So if I hook this up to a battery, I can calculate this. All this is here just trying to get you used to seeing this, so when I give you a problem that has a shorthand notation, or you see this, you're not like, okay, how do I read this? You're reading this left to right. This is showing you one half reaction, and this is showing the other half reaction. However, I could give you a problem like this, and you would still be able to use that to find these data. So the math we're doing here is actually really easy, but we're going to calculate the standard cell potential. What type of voltage are we going to get from these guys? So this voltage is electromotive force, but we're going to measure this guy in a unit of volts. A volt is a joule per coulomb. A coulomb, remember, is our electronic charge, the charge of our electrons. So how many joules per how many coulombs transferred? Joule our energy per coulombs. Once again, standard state condition for E naught is 1 molar, 1 atmosphere, 25 degrees Celsius. But no, so how we're going to calculate the E cell, we're going to look up two values on a table, and we're going to subtract them from each other. We're going to look up the reduction half reaction and the oxidation half reaction and subtract them. Specifically, we're going to subtract the reduction, or the oxidation from the reduction. We're going to subtract the left side from the right side of that half cell. And because there's no such thing as an absolute reduction potential, we're going to have an artificial 0 point. All these guys were measured in respect to 1 point, and we're saying that's 0. So when we look up on the table, the standard hydrogen electrode will be our artificial 0 point. The reaction of protons goes to hydrogen gas is where we set our 0 point. Is that really 0? No, but it's the measuring stick we use to measure everything else. Everything above hydrogen is positive. Everything below hydrogen is negative. Everything that is more reactive than hydrogen is positive. Everything that's less reactive is negative. Because we can't just go with the lowest number, because there could always be something less reactive than that we haven't found yet. So we're not going to try that. Here's another thing. When we look up these values, they're always given as a reduction. So we'd have to find this. So let's look at this. Cell potential tables are traditionally given as a reduction and as reduction potentials. The position of this table is usually based on the likelihood of being reduced or reducing hydrogen. So positive or negative. Now, the big thing here that's different from our delta G or delta H or whatever is when we subtract these guys, we do not need to take into account the moles. We do not need to take into account the balanced chemical equation. We just take the straight up values and subtract them. We just take the straight up values and subtract them. Full stop. We don't need to worry about anything else, because this is a joule per coulomb and not a straight up joule. This is like intrinsic, not extrinsic. So the coefficients will not matter. So in order to do this, 2 gold goes to gold and gas goes to 6 protons. You look up on the table, where is gold? You look very closely. You have fluorine, you have silver, you have cobalt, you have that peroxide, maybe cerium. I've already had that, but gold right here. Gold 3 plus 3 electrons goes to gold solid. That is 1.5. You have H2 and H plus. You keep going all the way down. That's right there at 0. You'll notice this is not H2 goes to 2H plus. This is 2H plus goes to H2. Remember, these are all given as reduction. Hydrogen is undergoing an oxidation. Hydrogen is undergoing an oxidation. So gold appears as it does in the table. Hydrogen does not. Hydrogen is the reverse. The one that is the reverse gets subtracted. So we'd say 1.5 minus 0. So what is the E cell of if I did this? If I put gold solution in my bubbled hydrogen gas through this, this would produce a voltage of 1.5 volts and would get a nice little gold solid. I bubbled hydrogen through there, I'd get a nice little gold solid. And we'll see when the E cell is positive, this is a spontaneous reaction. So that must mean when E cell is negative, it's non-spontaneous. So just to do this, I may not be able to easily switch between the doc cam, but I'll try. Cobalt 3 plus and silver goes to silver plus 1 and cobalt 2 plus. Then we have chlorine and chlorine and hydroxide goes to oxygen and water and Cl. 4Cl minus. We have, let's see, 2 copper plus 1. 2F minus goes to 2 copper and F2 plus, F2. And then 3 peroxide and our 2 chromium. That's water. Goes to 8 hydrogen and dichromate. Okay, so writing those down. So let's look. Cobalt 3 to cobalt 2. Please note there is more than one cobalt. You might have a cobalt 3 to cobalt 2. You might have a cobalt 2 to cobalt 0. You may have a cobalt 3 to cobalt 0. Find the one that matches your equation. Cobalt 3 to cobalt 2 is the third thing down at 1.82. 1.82. It appears as written. We can use that one as written. Silver, we do not use the second one. It's not silver 2 to silver 1. We need to keep going down. Where is silver 1 to silver 0? Silver 1 to silver 0 is right below mercury. I'd like to say that's 0.8. Let's say it's 0.8. It is opposite of how we have in the equation. So what we're going to have is 1.8 minus 0.8. So going to the dot cam just real quick. We have 1.8 minus 0.8. So our cell potential is just going to be 1.02 volts. Straightforward. Straightforward. Now, the next guy, chloride. Where's chloride? Normally this would be where you could help me, but chloride right there, right below lead oxide. I do believe that's 1.36. It is identical as written. Of course, we've doubled the chlorides in my equation, but it's identical as written. Now I need oxygen and water goes to hydroxide. Oxygen and water goes to hydroxide. Not oxygen plus protons goes to water, which is pretty close to the chlorine. Keep going, keep going. There's oxygen plus protons goes to peroxide. There we go. Top of the right column. Oxygen plus water goes to hydroxide at 0.4 volts. It is opposite as written, so that's the one we're subtracting. So 1.36 minus 0.4. That's going to be what? 9.4? Oh, sorry, 0.94. 0.94 volts. You don't need to double this because there's 4 chlorides. You don't need to double this. You just literally use it as given. You literally use this as given. 1.36, I pulled off the table. 0.4, I pulled off the table. Subtract the 2. Okay. Looking at 2 copper 1 plus goes to copper solid. So that's at the bottom of the table of the left column. That's 0.52. And then we have fluorine goes to F2 minus. That's the top. 2.87. That is opposite as written. That's opposite as written. But for this chemical reaction, we have to use it. This is the chemical reaction we're studying, so this is the one we have to use. So 0.52, 2.87, we get negative 2.35. As we'll see in the future, that guy, this is because this is an electrolytic cell that we can put power in to force it to do it, but it will not happen on its own. It is a non-spontaneous. And the last one is a massive beast. Thank God we just did this problem, because the 1/2 reaction is hidden by the other half reaction. We did this. Hydrogen peroxide goes to water. But you don't see the water's on the left, not on the right. Remember, we did this one and the water canceled out. So that one's actually what, like 1.78? 1.78. And it just so happens it's canceled out by the chromium one, which is right there, 1.33. Sometimes one half reaction helps cancel out the other half reaction and makes it a little harder to find. So this last one, 1.78 minus 1.33, means our voltage is 0.45 volts. But we're literally just taking the two numbers and subtracting them. Two numbers and subtracting them. If I have a negative value, I would subtract a negative, which is the same as adding a positive. But as I said, this is a little bit different, but not necessarily different hard. You have to find the numbers from the table. No, yeah. You have to find the numbers from the table, and you just have to subtract them. If you can do that, you can find the cell potential. That's where we're going to stop for today, but we'll have next week, we'll start to see how cell potential directly relates to our Gibbs free energy. And then we're going to finally relate it to, we're going to talk about electrolytic cells. We're going to relate this to K and Q, and then talk about electroplating, the process by which we put a metal onto some surface using electrical work. With that in mind, I want to thank you for your time. You can come get your tests at any point. See you guys either in lab or on next Tuesday.